Welcome to this screencast in which we cover the topic of discrete random variables. Random variables can be either discrete, continuous, or mixed. A random variable is defined as discrete when it can take values only from a countable list of distinct values, or in other words, is defined on a discrete range. Here are a few examples of discrete random variables. As first, we can look again at the random process of rolling a die. If we define the random variable x as the number on the top face of the die, it's pretty easy to see that this random variable can only take integer numbers from 1 to 6. And since this list is finite, x is a finite discrete random variable. As a second example, imagine you buy straws from 4 different brands and you define the random variable z as the length of a straw in centimeters. Maybe you find out that the only values that z can take are 18.7, 19.2, 19.5, and 18.5. Here again we have a finite list of distinct values, so z is a finite discrete random variable. As a last example, we define y as the number of years before the end of the world. Y can take any discrete value from 0 to infinite. So in this case, the list of distinct values is infinite, and y is an infinite discrete random variable. After having built some intuition on what is a random variable, the question may arise on how we can describe random variables from a mathematical point of view. One way to do so is by using probability distributions. Probability distributions are functions that associate to each possible outcome of a random variable a probability. Let's come back to the example of rolling two dice and the random variable y given by the sum of the values on the top faces of these two dice. One way to provide the probability distribution of y is by a table, like the one shown in the slide. This table shows for all the possible combination of the 1 and the 2, the associated outcome and the probability of obtaining that outcome. Already the second and the third column of the table represents a probability distribution because it associates a probability to each possible value that y can take. Another way to show a probability distribution is by plotting the histogram obtained for a sufficiently high number of trials. In fact, by the frequentist definition of probability, the relative frequency is equivalent to the probability when n is very high. It basically describes how the probability distributes over all possible outcomes of y. The probability distribution we were describing in the previous slide, they were actually a probability mass function. The PMF is defined as the list of all possible values of x together with the probability of obtaining that value. The PMF is all defined for discrete random variables and has the following properties. The PMF is equal to 0 for any x that is not in the range. The PMF is bounded between 0 and 1 as a direct consequence of the first axiom of probability. The last property states that the sum of all PMF values for x in the range is equal to 1, and this is a direct consequence of the second and third axioms of probability. The second axiom states that probability of the sample space is equal to 1, while the third axiom states that the probability of the sum of n disjoint events is equal to the sum of the probabilities of each single event. Since each x in the range is a disjoint event and all x's in the range represents the sample space, the sum of this probability is equivalent of the probability of the sample space and therefore equal to 1. Another important probability distribution is the cumulative distribution function, in short CDF, which is defined by the formula in the slide. The CDF can be defined for discrete random variables when they are ordered continuous random variables, and mixed random variables. Since it is a probability, also the CDF is bounded between 0 and 1. The CDF of minus infinity is 0, and the of plus infinity is equal to 1. This is easy to understand when we look at the definition of CDF. The event x smaller or equal to minus infinity basically represents the null event because nothing is smaller than minus infinity, and therefore the probability is equal to 0. By similar reasoning, the event x smaller or equal plus infinity is the sample space, and therefore the CDF at infinity is equal to 1. The CDF is an increasing function, so it cannot decrease for increasing values. Finally, the difference of the CDF calculated at two different values, x1 and x2, is equivalent to the probability of x being between these two values. An interesting relationship between the CDF and the PMF is that the CDF can be obtained from the PMF by using the formula in the slide. This formula states that the CDF at any x is obtained by summing all values of the PMF for any xi smaller than or equal to x. For example, in the slide we have a PMF provided by the stem plot. To obtain the CDF at 0, I need to sum all the PMF values for k equal or smaller than 0. In this case, we only have the value at 0, so the CDF at 0 is equal to 0.18, exactly as the PMF at 0. For 1, I will sum the values at 0 and 1. For 2, I will sum the values at 2, 1, and 0, and so on for all the rest of values in the range. Looking at these stem plots, we could do a quick sanity check to verify whether these are valid probability distributions. Focusing first on the PMF, we see that the maximum value is 0.35 and the minimum value is 0. So the PMF is bounded between 0 and 1. Although it is a bit difficult to see from the plot, the sum of all PMF values in the range is equal to 1. So we have no reason to believe that this is not a PMF. Now looking at the CDF, we can also see that the CDF is bounded between 0 and 1, and we can also easily see that it's an increasing function because it's increasing for any increasing k. Finally, we can also extrapolate that the CDF for minus infinity is equal to 0 and the CDF for plus infinity is equal to 1, confirming that this is a valid CDF. This ends the screencast on discrete random variables. Thank you for your attention.